Yeah, welcome everybody. I'm very happy to introduce Constantine Caramanis today. So he's professor at the University of Texas at Austin. He did his PhD at MIT and also an AB in mathematics in Harvard. And yeah, his research is focused mainly on decision-making in large-scale complex systems with statistical analysis and optimization. So for me, he's very well known as the founder of what you would call today K-adaptability in robust optimization, and also did a lot of research on the intersection of robust optimization and machine learning. So I'm very happy to have him here today, and please, Constantine.
Thanks very much for the introduction, and thank you for the invitation to talk to you all today. So I'm going to tell you a story that I've been working on for a number of years, actually, with and mainly with these three collaborators that I have pictured here. Jongyo got his PhD at UT, which is how I was fortunate to meet him. He's now a postdoc at Madison. Yoni, he's a researcher at Meta, and Shai Manor is a professor at the Technion in Israel. And as Jan said, I've been working on optimization and uncertainty in different models for that for some time, and actually for a number of years we've been thinking about mixture models, which is a basic modeling tool in optimization and machine learning, and we're always thinking about how we can build up more complex real world type models from smaller building blocks, and mixtures are one of them. And this is really that story here as well, but moved to the setting of dynamic decision making. So let me start with an example that I have in mind. This talk is not going to be about any applications, because I haven't had the good luck to be focused on any, unfortunately. But just to fix ideas of what I'm talking about. So, what is contextual reinforcement learning, or how do I think about it, and how does that relate to the title of this talk? So imagine that our goal is to treat patients, and when I say treat, I'm thinking about some treatment that maybe requires multiple visits, or treating someone over time, the same patient over time. And how do we do this? Patient comes into your office. I'm not a doctor. Probably nobody in the audience is, but we can guess. And what we try to do is we use, the doctor would use context. So what is the context in this case? Even though every person is an individual, there are certain things that allow us to group patients together, and so learn across patients, and therefore improve better, as opposed to a universe where every single patient has a completely unique response to use your diagnostic labs or your medical history. And essentially what this allows us to do is to cluster trajectories. And by clustering, that means that for two trajectories in the same cluster, they should have similar behavior, similar statistical behavior. Now, this talk is wondering if this clustering exists, but we don't have that signal, can we still take advantage of it? So in a way, this mixture is a question of can we take advantage of a world where things really are clustered, but nobody tells us what cluster we're in to do better. So, for example, in this case, I mentioned on the previous slide that diagnostic labs might be might be part of the context, but it's easy to think about what we don't get to see. So essentially anything that you don't know about your patient, you can think about a kind of, you can think about something that would have allowed us to cluster had we known, but we don't know. So for example, your doctor may not know if certain your genes are activated or not. I shouldn't probably, talk in too much detail, otherwise I'll reveal more about my lack of knowledge of the medical profession. But hopefully you get the idea. And just to give a different example, suppose that you have an online platform and you're serving users and you interact with users for some time. For example, a recommendation system. And you know some things about your users, maybe some things they volunteer, but there may be other things that you don't know that would have allowed us to cluster had we known them. So again, the setting is that there is a label that where users or trajectories do cluster according to that label, but we don't get to see that label. So this is the setting of this talk, and I want to know how well can we do without knowing that. So one of my main points here is that this kind of partial observation is a real problem. I would say it appears in virtually every setting of practical interest. We don't know absolutely everything about the user that we're interacting with, but in particular, this talk is not about the general PUMDP problem, which is a long history and has been extensively studied. There's something quite special about my setting, which gives me hope that I'll be able to sidestep some of the traditional complications or impossibility results that have been around for decades for PUMDPs, and namely that is that in this case, what I don't observe is fixed, as opposed to having a state in a Markov chain, and I only observe a projection of it, and I can never know what state I'm in. So in the medical treatment example, I'm dealing with the same patient. So I may not know everything about my patient, but I'm dealing with the same patient. So the unknown part, the latent part, is not changing over time. And similarly, in a recommendation example, or in any setting an online setting where I have one user and I have an interaction period greater than 1. Okay, so the problem that I have in mind would be naturally called a latent Markov decision process, a latent MDP. I'm not going to. If I use this notation again, I'll try to repeat it, but just because I'm stating the model, I thought I would show everything. Most of it is standard here for an MDP, except for the subscript M. The subscript M is that latent variable that I don't get to observe. So in other words, here there are, and I also realize I've overloaded the letter M for the number of contexts, M for MDP, and later on M for moment, but hopefully we'll be able to track that. But everything else here is standard. Each individual MDP has a state space, an action space, transition, initial state distribution, reward probability. The one important parameter that will come up again is H, and that's just the length of the interaction. So I get to see every patient for H steps. I get to interact with every online user for a horizon H. And at no point am I given access to M, which would be the label of which MDP am I dealing with? What was that hidden label? This kind of model has appeared under different names in a variety of different contexts. I've put some of these here on the right: multimodal MDPs, multitask MDPs. In particular, the setting that I have in mind is the case where M is small. So M, the number of different contexts, so the number of environments is not huge. In particular, I'm not going to allow M to scale. And I'm also interested in the setting of a relatively short time horizon. So, I mean, and in particular, one reason that I'm interested in this setting is this is the setting where we're not going to have the chance to learn what little m is. So if h were going to infinity, we could imagine that we would just spend the first portion of that horizon figuring out, estimating what the latent variables are. And since we then have the luxury of them being fixed, then for the rest of the time, I could just play optimally as if I just had been given the label to start with. So that's not the setting that I'm interested in. I'm interested in the setting where h, the horizon, is typically going to be too short for me to be able to learn anything. And so my goal is to learn near optimal policies for this model. In particular, I want to make clear, and I'll mention this several times in the talk, I'm interested in sample complexity here. And if someone were to give me all of the parameters of the model, this is still an interesting and hard problem, because still, so in other words, if I knew what the transitions were for each label, what the rewards were for each label, if I knew that ahead of time, if this is still the planning problem is still difficult. And there's been a lot of work on that. And I'm not going to address that at all in this talk. So if I can ever get to a point where I've learned the parameters, then my problem for me is I consider that solved, because I'm just going to use a planning algorithm that is already available. So I'm interested in the setting where we haven't been able to estimate those parameters, and as later in the talk, I'm interested in a setting we just cannot estimate the parameters. And okay, so what's the main challenge? At a high level, the main challenge is that whenever we lose full observation, we lose Markovianity. So in other words, the optimal policy that we have can no longer just depend on the state that we see. And it's going to also depend on our best estimate of what we don't know. And then the estimate is going to use the entire history. So this makes things difficult. It makes things difficult from a computational standpoint, but as far as I'm concerned, again, I'll be focused on sample complexity. So again, just to kind of make this crystal clear, if I had the contextual information, so someone said you're in Markov chain little m equals 1 in the first line in this example, or whatever, little m equals 3 or little m equals 4, then the probability that I receive a particular reward or make a particular transition conditioned on the entire history is just equal to the probability only conditioned on the state that I'm in and the action that I take right now. And we just don't have that. We no longer have that luxury if we don't have the information. So in other words, we can't ignore the history of what we've seen. And so in general, this is a hard setting. And in general, it requires either some strong assumptions to sidestep it, or otherwise we just have to pay exponential sample complexity and potentially exponential computational complexity. I'm going to be interested in a specialized version of this problem where I don't have the good luck of having a signal or any help about learning what my latent variables are from the transitions. So in particular, the state transitions are going to be common. We could potentially imagine a setting where the state transitions could actually help us. So we could imagine a different class of problem of latent MDPs where we have a condition on, say, distance between transition probabilities, and that this would actually help us. So in this case, we don't have that. But in general, of course, this is going to be a special case of the latent MDP, of the general latent MDP problem. So I'm going to call this reward mixing. So in other words, the only thing that I don't get to, the latent variable doesn't control the transitions, it just controls the reward. So here's an example of where this might happen. Imagine that again, back to my medical example, that different treatments have different side effects. So there could be a particular treatment which causes, which is involved in somewhat more pain for the patient, but doesn't cause any drowsiness. Whereas another treatment might do a better job at taking away the pain, but might cause lethargy, drowsiness, and so on. Because the assumption that the transition probabilities are the same means that each of these treatments is going to have the disease itself will take the same statistical trajectory regardless of what the label is of the patient. But imagine that I have now two different patients, one that is very active and has a high pain tolerance, and the other who has a very low pain tolerance. So you can see that what I'm trying to build up here is this example where one patient might prefer, so might give a higher reward to the treatment that doesn't promote drowsiness, and the other one might prefer the one that has less pain. So this is the problem that I'm interested in. The different labels are telling me nothing about the transition, so they don't affect the transition, just the reward. Okay, so this is very similar to the slide I showed you before, but you'll just notice that there's no little m subscript on t, which we had before. So the transitions no longer depend on the label. It's just mu sub m, which is the parameters that determine the statistics of the reward that I get. So those are allowed to depend on the label. And the main question, again, I want to understand is that of sample complexity. How many samples do we need to learn a good policy? So as a first thought, we can ask, so let's look at the extreme case where h, the time horizon, is just 1. So is this an easy or a hard problem? You can take a second to think about it. You might think, wow, this is probably the hardest setting because you have absolutely zero chance of estimating anything. But, and this is the point that I want to make here, that actually this is an easy problem. Yes, you can't estimate what m is, so you certainly have no chance of doing as well as the genie who knows that. But it's quite easy to see that that you're going to find the best policy, because the best policy doesn't need to know any information about little m. All you can ever learn about this problem, the only thing that's observable about this problem, is expectation across all contexts, because you only have one interaction. So in other words, this h equals 1 is an easy problem because I can't take advantage of this clustering at all. I can just do what's best on average. I can't hope to do anything better. So even if the best policy is not very good in the sense of comparing with the genie that knows the latent information, still we can see that we can easily find the best policy. So the settings that are interesting, the non-trivial cases, are when we do have a small interaction time. Again, small because I don't want to be in a setting where I can learn what the label is. There's been a lot of work and a lot of recent POMDPs have a very long history. I'm not going to talk about the older results, but there's been a lot of recent results on the positive results, not impossibility results, that tell us when we can hope to have finite sample complexity, polynomial sample complexity for POMDPs. And essentially, in some of the recent results that I find quite exciting, essentially what they require is that even if I can never estimate what state I'm in, if I'm in a setting where eventually in my trajectory, I can estimate the full state some time ago, then you can estimate an epsilon optimal policy in polynomial sample complexity. So I've given some of the references here for that. This I'm interested in an interaction that at any point during the trajectory, even at the end of the horizon of my interaction, will I be able to estimate what that m was, what that little m was. In a separate work, which maybe I'll have a chance at the very end to mention a few words about, if you do have the ability to learn, even at the very, very end, what the true label was, then actually you can do a lot better in a more general problem. So I'm interested in the setting where we don't have. So let's think about, what could we possibly do in this case? Why can we hope that we can make progress? Oh, and I should say, in case it's not clear, I mentioned why the results by these in this direction aren't useful for us. But what we have is we have a different kind of structure that we want to exploit, and the structure in this setting is that the latent variables are constant, so they're not changing. So just as a simple case of why do we hope that we could do well. Okay, so a little bit of a reminder of what notation is here. R is R for so expectation of RI, the expected reward we get, and just to kind of simplify, at some points I've used X to denote the pair of state action. Right, so in this case, VI is equal to the expected reward you get conditioned on being in XJ, which means the tuple of state SJ and having taken action AJ. So this is what this means. So if so what do we need to know for the m equals 2 case? Capital M in this case is the number of contexts. So I have 2 types of patients. And you can see here that if I'm able to take expectations at a single state action pair and then at pairs of state action pairs, so Xi and Xj, so I can learn first and second order moments, well then, if I could actually learn this, then I'm in business, because if I could compute this imperfectly, or even approximately, then you can see that that I can essentially compute a rank 1 matrix whose and if I factorize that, I would be able to find mu1 minus mu2. And then since I know mu1 plus mu2, I know this would allow me to learn the parameters. So that's pretty promising. And essentially, this is the basic idea that we take advantage of in, for example, like Gaussian mixtures. Unfortunately, that's not the whole story here. We're actually quite far from that. But still, this gives us hope that we have some approach. So again, how would we make this happen? Ideally, we would have this. We'd approximately know these 2 moments, mu1 and m1 and m2. But unfortunately, it turns out that we can't even hope for that. So even this estimation of the moments is challenging. And just a simple picture tells the story. So imagine that this is your Markov chain. What this really means is that in no trajectory will you ever be in state 2 and state 3. So in particular, you're never going to get Xi and Xj when I equals 2 and J equals 3. So that means that we can't really hope for something as simple. More generally, and what you can imagine that in addition to having some moments that you can't compute at all. Some moments might be much more difficult to estimate probabilistically. So there might be some sequence of states which you can get to in one trajectory, but might be much, much less likely, no matter what you do, no matter what policy you take, than other states. So that means, and we're going to see that this is going to play an important role, that we'll have very different accuracies for different moments. So we'll be quite far from a uniform estimation of our moments, beyond just not being able to compute them exactly. But for n equals 2, we can actually make some progress. So it turns out, and I won't give the details here because I'm interested in the more general case, which subsumes this. But it turns out that even if we have non-uniform estimates of the moments, we can compute the parameters mu1 and mu2 approximately, trying to solve a robust or noisy version of this equation at the top of the slide. And there, what's important to show is that the parameters that we're unable to estimate don't really matter. So in other words, for this example that I gave, we're not able to estimate the second order moment 2 and 3, but you can also see that it doesn't really matter since you're never going to visit 2 and 3 in one trajectory. But let's see, what. And here are the basic results for the setting where you just have 2 latent contexts. I care about sample complexity. So K is the number of samples. So the result says that we can learn a near optimal policy, and the number of episodes we need is quadratic in the number of states and quadratic in the number of actions. So it's quadratic in S times A. And actually, this is up to some factors that depend on H and epsilon and eta. This is the best that you can do. So this is the best. This quadratic dependence is the best that you can hope for in terms of your dependence on the state and actions. So let's turn to the more general setting where you have many contexts. So not just 2. And the question is, how can we leverage the higher order moments when m is greater than 2? So there are several things that are different here. Right away, we see that there's no analog to this kind of equation. Although it turns out that that's not going to be that important for us because we're not interested in the computational aspects. But an important thing to note that there's no analog to that kind of decomposition. The main challenges are that we can't estimate all the moments of the same accuracy, some not at all. And this becomes more pronounced for higher order moments. And then even if you could estimate, the parameters are not going to be identifiable. For the m equals 2 case, some of the parameters, it wasn't exactly that the parameters were identifiable, but the ones that were important were identifiable. So that was the basis of that previous result. I didn't go into the details, but we don't even have that. So my main point is that we need some other kind of thinking, that we can't focus. We need to get away from this idea of parameter recovery or approximate parameter recovery. We can't have that. In other words, if I estimate for any sample complexity that I'm allowed, I'll do my best to estimate these higher order moments. And those higher order moments are going to be consistent or nearly consistent up to statistically consistent with parameters that are very, very far from each other. So it's in this specific sense that I can't hope to do approximate parameter recovery. But after all, parameter recovery was never the name of the game. It was just an avenue that I used for the m equals 2 case to say that if I have parameter recovery, then I can get a good policy. But all I actually want is a good policy. So we try to take a different approach. And the idea is can we just jump over recovery, leap over that, ignore that, and argue that if the moments are close of two models, I've called here the models script M and script M hat. We can think of the hat as being the estimated model, but actually everything I'm going to talk about holds for two models, M1 and M2, script M1 and script M2, even if they have a different number of latent states. So what we're going to show is that if two models, M hat and M, or M1 and M2, if they have moments that are close, then actually they're close in total variation. That means that they're going to essentially have the same behavior, output behavior, for any given policy. And that's all we need. So this first displayed equation is basically saying that models M and M hat for any policy that you have are the probability that they'll take any given trajectory is going to be very close. And that's all we need, because if M is script M as model, and you give me an M hat model, even if the parameters are very far from the true ones, if M hat is very close to to M in total variation in the sense above, then I can find an epsilon optimal policy for M hat, and that's going to be nearly optimal for M as well. And that's basically the name of the game. So in other words, the roadmap here is I want to find a way to compute moments to a non-uniform accuracy. I'm going to find a model that matches those moments or nearly matches those moments. We know that one exists because the original model nearly matches those. So at least the true model does. So that perhaps there are others, but certainly one exists. And note that I'm not saying how I'm going to find this. And again, this is one reason that this isn't a talk about computational complexity. So I'll assume that if I can't think of anything more clever, I'm going to do a brute force search to find M hat and just verify that it matches moments. So I care about sample complexity. And then I want to show, what I need to show is that if all I know about M hat is that it matches moments that were generated by the true M, so in other words, M hat and M are close in the moment space, then they're also close in total variation. And the bold is what I care about, what I care to show. Everything else is just kind of putting pieces together. Okay, so let's see where we are. I said we can't get a uniform bound on the different moments. How well can we estimate moments? Roughly speaking, if you visit a given trajectory, say state 2 and 3, if a trajectory passes through state 2 and 3, how well am I going to compute the second order moment 2, 3? Well, this takes a little bit of, but essentially standard concentration results are going to show that if I count the number of times that I take trajectories that include states 2 and states 3, then my accuracy in the moments of 2 and 3 are going to be like 1 over the square root of the number of visits. So n of x here is the number of times in my the number of trajectories that I see that visited the states contained in bold X. And so all this is not something magic here. It's exactly what we would expect. But this is how well I can estimate moments. And so if you can never visit a particular sequence of states like 2, 3 in that example, that little example I showed, then n of x is 0, which means you can't estimate it at all. And the more that you can visit a particular set of states in one single trajectory, the higher n of x will be, and therefore the better your accuracy will be. So essentially, this is the kind of accuracy that we can expect. So I want to know, the main question for us is, how can we use these moments despite this non-uniform uncertainty? So here's the basic thought of what we're going to do. I'm going to group all possible trajectories conceptually. This is not part of any algorithm, but I'm going to group trajectories based on how frequently I visit them. And I'll bin this, of course. So on the left here, I have E0, which is, you think about the trajectories that you visit a lot. And then E1 are trajectories that you visit less. We have a specific sequence of, so less means that it's given by this number n sub L here. So N0 is the number of times I visit trajectories in E0 and so on down. And we won't get into the exact details here, but roughly these n's satisfy a geometric relationship. And the main observation is this: if we look at the displayed equation here, the quantity on the left is the total variation between the true model and the estimated model, P and P hat. I'm just saying that I can write this instead of summing over all trajectories and computing the probability difference as computed by the two models. I can just write that sum as, first I'm going to sum over everything in E0, then I'm going to sum over everything in E1, and so on. And so what this means is that I have this internal sum is only over trajectories that are visited the same amount. And that means that every moment that corresponds to those trajectories will be estimated to a similar degree. Now, so this inequality that I've written here is relatively straightforward. The main question for us is, what is the statistical distance among trajectories that are visited the same amount? How big is it? So in other words, how big is this epsilon L that I've written? That's the statistical distance. I don't know that. I don't assume that I'm given that. What I assume I am given is the distance between moments. So in other words, if delta L is my accuracy for the moment, so I know that for any x in one of these groups, say, I don't know if you can see my mouse. I'm kind of using it, but I'll try to make sure I'm saying it in words. So if the first bullet here, if for every x in E sub L, that's one of those groups that's visited the same amount, I know that I have a uniform accuracy on moments. All those moments I've computed to accuracy at least delta L. And I also know that I can, there's also a statistical distance between, so in other words, the total variation restricted to all of those trajectories that are in EL. So the main challenge here is to relate these two parameters. I know delta L because I get to design that. I get to choose a sample complexity, a sample budget, and that will tell me how many times I can visit everything in E0, everything in E1, and so on. But what I want to know is, how does that relate to statistical closeness? So what links delta L and epsilon L? And that is the main, showing that that relationship is controlled is the whole part, is the whole technical heart of showing our result. Okay, and this is a summary of the main results that we need. It is really the first bullet, which is the main result, and then the others are the other gluing parts that we need together. So maybe we can start in the reverse order. At the bottom, I have this lemma. I already talked through this. This is basically saying that if you visit a certain sequence of states n of x times, then the accuracy that you'll have in the moments is about 1 over the square root of that. So again, this is pretty much standard. The other question that we need, this is the second proposition before we get to the main result up top, is how do we use our whatever budget we have? K here is our total budget. And how can we use this to explore different these different trajectories? Because what I didn't mention, but is probably it's in the text, and probably you've guessed it, is that I need to count these. I need to have these accuracies in terms of any policy. So in other words, I need to think about how much I'm visiting how much any policy would visit a particular trajectory, not just my policy, because I don't know what policy I'm going to end up with at the end. So I need to make sure that that when I'm making this division here of frequently visited, well explored, and underexplored, each trajectory is well explored or underexplored with respect to the policy that tries to visit that trajectory as much as possible, as much as it can. So this takes a bit of technical work as well, but there is a main tool that exists in the literature that's called pure exploration, which involves making a higher order Markov chain and essentially ignoring rewards and running a pure exploration policy on that. I'm not going to go into the details of that right now, but perhaps we can talk about it later. So the main result that I want to point to is this first proposition that basically says that delta L and epsilon are related in this linear way. So if I have accuracy on the moments of delta L, remember L is telling us which group are we in, highly visited or less visited. Then within that group, epsilon EL, the total variation distance is going to, I called it epsilon L before because I didn't know what it was. This proposition tells us what that statistical distance is. And it is this term here at the end of the first displayed equation, delta L, so it's linear in delta L, times 4hz to the d. That's in a way the main result. And now putting these pieces together, this tells us that the general sample complexity scales in this way. So the number of episodes that you need scales like S to the D, A to the D, where D is the minimum of H, which is the horizon. And here I wrote M1 and M2 to give a slightly more general result. M was the number of latent states. But actually, the main result I wanted to show, and the main result the first proposition says, is that if two completely different MDP RMMD reward mixing MDPs with potentially different number of latent states have this kind of moment closeness, then this will be their total variation closeness. So M1 and M2 were the number of latent states in one in each of these. If I'm just looking at at M and M hat, the estimated model and the true model, then M1 and M2 are the same. So D is the min of 2M and H. So this is a result, and it tells us that, first of all, we recover the results for the first case that I showed, but also you say, okay, this looks pretty expensive, and that's true. We have this exponent of D, and this basically is telling us that you can only really hope to learn this if you have a small number of contexts or if you have a short time horizon. And let me show, looking at the time, let me just skip over the result of the proof and just show that there's a lower bound, which is telling us that this exponential dependence is unfortunately correct. You'll see that there's a gap here because in the positive result that I showed, we had SA to the essentially 2m, minimum of 2m and h. And this is saying that you really can't hope to do anything better than a square root dependence of m, the number of latent contexts you have in the exponent. So this result is telling us that it's possible that there could be some improvement here in the exponent, but you're going to have an exponential dependence. It's not going to be polynomial in M, and the dependence on epsilon again is as we would hope for. You can't improve that. I'll just say just a word about well, I won't say more about the proof. The proof is is a proof by induction, and maybe if there's time afterwards, I will talk about it. A few other thoughts just to kind of wrap up the talk, and then I'll be happy to take any questions. Actually, I should have said I'm happy to take any questions at any time. We could also think about other things, other assumptions that would potentially make the problem easier. And of course, we've been, especially since there are lower bounds as well, we've been thinking about what does this tell us about what kind of problems we can solve. So far, this has told us that if M is quite small, if you have a few latent contexts, then you can hope to address this problem. We haven't asked anything in terms of the general. Whenever you think about a clustering problem, even clustering Gaussian mixtures, usually hardness results there are indexed by how far apart the means are of the clusters. And again, here you can make your life easier in that way. Notice that we haven't required that at all, which in one way is why we end up with results that require m, the number of contexts, to be small, or otherwise you pay an exponential price in them. So if for example the reward parameters are far apart from each other, or at least they have a gap, then in a recent result, we looked at the setting where you just have bandits. So this is the setting where you have a contextual bandits, but you're not told the context, but you have an opportunity to interact with the same context several times, even though you're not told that context. So in this case, we get a purely polynomial bound, but it's using these additional properties. And we could also ask for let me skip that slide. The more general latent MDP problem, where the transitions might also depend. So in that case, this is actually how hard it is. We found a lower bound that's exponential in M, not the square root of M. But again, note that this is now a more general problem than the reward mixing, because the latent variable is also allowed to affect the transitions. So this is kind of where we started. To wrap up with a few of the takeaways, I think one of the reasons that I find this work interesting is that we try to make progress in the setting where we're not essentially splitting the problem into estimate the latent variable and then do the best that you can with that estimate. So in general, we're interested in this talk, and these results are about the setting where you just can't identify the latent model. I'm not making assumptions about separability or other other tensor-like assumptions that people have used in different settings, latent settings, which essentially allow you to identify the latent variables. I think there's a lot of interesting future directions, being of course cognizant of the lower bounds. It seems like a small m is important, or stronger assumptions are important. So those are the two avenues that are really left for tractability. For LMDPs, we have this exponential lower bound, but actually we don't know what to do when m is very small. So we have this lower bound. Now that tells us that potentially for m equals 2, this is a problem where you can make progress. We've solved that when the transitions are the same, but aren't clear exactly what to do when the transitions also depend on the parameters. And then there's a lot of other interesting directions that can be combined with this latent setting that I think are interesting. I'll stop there, and I'm happy to answer questions or maybe talk about the proof if as people have time. And of course, I'm happy to talk offline to anyone who's interested in this direction as well. So these are a few of our, as I said, this is a story that we've been working on for some time, and are continue to be excited about. Thanks for your attention. I'm happy to answer any questions that you may have.